We're going to look at problems when we are mixing some kinds of solutions with other kinds of solutions. So we're going to start out with a solution that has water and some chemical. I'm just going to call it chemical. It could be salt or fat or anything that mixes with water well. I'm just going to call it chemical. And there's a few things we can do. We can add, we're only going to focus on adding things to this. We could, it shouldn't be too difficult actually, to remove and replace some of this. By the way, we're assuming this is thoroughly mixed up. So I'm drawing a picture where the chemical and the water are separated, but in reality, this is all mixed. This is just to give us an idea that there is some chemical and some water. Now we can add, one thing we can do is add pure water, and that will dilute this. It will water it down. Or we could add more chemical, more pure chemical. And that will increase the concentration of the solution. So this is a solution which is made up of water and a chemical. And we can add more water to dilute or water down the solution, or we can increase the amount of chemical but then that will also increase the volume. But that is okay. And or we can add another solution with less concentration than this solution. So we can add a less concentrated solution. And that will also water down this solution. Or we can add a more concentrated solution. And that will increase the concentration of the solution, the chemical rather, in the solution. Whoa. So we're going to focus on only those 4 problems. There are many more problems we can make up and we could focus on, but those are the only 4 we're gonna attempt. All right. So we're gonna have 4 examples, 4 of them. Yeah, we're gonna start. Okay, so we're gonna start with 10 gallons of a solution that is 5% a chemical. I'm just going to call it a generic chemical. Again, it could be some kind of salt or some kind of, to be perfectly honest, I do not know much about chemistry. So I do not know what mixes with water very well. I think proteins do. So maybe some protein. But I'm just going to call it generically some chemical, a chemical. There we go. So we're going to start with 10 gallons of a solution that is 5% a chemical. And consequently, oftentimes we don't tell you the second part, but if it is 5% chemical, the other part would be probably just water and 90% water. So if we tell you one, you know the other one. Okay, and we typically don't tell you the 2 of them. We just tell you 5% of the chemical, and it is implied that the other 90% is going to be the water. All right, so we're going to do 4 problems, and we're going to start with this. All right, so that is the starting, and the first problem. Let's label this as a Roman number 1. And then we're going to have 4 examples that branch off of this. So example 1. Okay, so the question is, how much pure water do we need to add to obtain? Okay, so if we are going to add pure water, that means that the concentration is going to go down. Instead of 5%, it is going to go, it is going to be reduced. So we want something that is less than 5%. So how much pure water do we need to add to obtain a, let's say, 3.5% concentration? Okay, question mark. All right, so we want to water this down. For some reason, we don't want it to be too strong, the solution. We want it to be less strong. And so, so how can we do that? All right, so the first thing to notice, and I'm going to back up a little bit to here, is that if you have 5% of the chemical and you have 10 gallons, then we can compute the actual volume of the chemical. 5%, 0.05 is 5% of 10 gallons. All we have to do is multiply this out. And so these are the gallons. And that is the percentage of the chemical of those gallons. And if we multiply this out, we get 0.5. And those are going to be gallons. So we're going to have half a gallon of pure chemical. So when you have 5% concentration in 10 gallons of the solution, half a gallon is pure chemical, which has been completely dissolved in the water. So you cannot really separate it anymore. It's all mixed up. But you can add more water and keep mixing it up to water it down. This, if we add pure water, this 0.5, this half a gallon is not going to change. It's already there. And then we're going to pour more water into this container. And so this half a gallon is going to be used up for more of the liquid, more of the solution. Okay, so how do we set up our equation? Okay, so first we need to know how much pure chemical we have, and we already figured that out. That is half a gallon. So the concentration of, all right, so the pure chemical is going to be half a gallon from the previous step. All right, we're going to add water, so that means that we're not going to add more chemical. And this is going to, and the total number of liquid, the total amount of liquid we're going to have is the 10 gallons plus whatever X number of gallons of water we're going to add. So in this case, we're going to assume, we're going to set X be the number of gallons, of added water. There we go. All right, so we still have half a gallon of the chemical, but now we got the 10 gallons of the solution to start with, plus a whole bunch of water. And that is a ratio, that is a concentration. And we want this to be 3.5%, which is 0.035. So there's our equation. If we're just adding pure water, this is the way we set it up. Mind, we figured this out in here when we were setting up the problem. Okay, now it's a matter of figuring out what X is in this case. So multiply both sides by 10 plus X. We end up with 0.5 equaling 10 times that. So that is going to be 0.35 plus X times that. So that is 0.035x. Okay. Subtract 0.35 from 0.5. So we end up with 0.15 equals 0.035x. And then we can divide by this coefficient. So, and I'm going to switch those two around. So x is equal to 0.15 over 0.035. I'm going to multiply by 1,000 to get rid of the decimal point. We typically want to end up with fractions. So 150 after we multiply by 1,000 over 35. And then we can divide by 5. If we divide by 5, we get 30. And dividing this by 5 gives us 7. And 30 over 7, if we turn that into a mixed number, we divide 30. How many times does 7 go into 30? Well, 4, because that gives us 28. 4, and we're left with 2/7. So this is the number of gallons. Okay, so we need to add 4 2/7 of a gallon more of water to water down 10 gallons of solution, which have a concentration of 5%, down to 3.5%. All right. Okay, so we need to add 4 and change gallons, less than 5 gallons of pure water, again, to reduce a solution that is 5% of a chemical down to 3.5% of a chemical if we just add pure water. Example 2. Okay. So now we're going to add, well, how much of a 2% solution do we need to add to obtain a, again, 3.5% concentration? Mind, we're still working on the same assumption that we started out with here, that we have 10 gallons of a 5% chemical concentration. 10 gallons and 5%. And now we have this example. We're adding pure water to get a result. Now start all over with this. And now we're going to add a solution that is not as strong. It is less strong. It is 2% of the chemical. Now, if we are adding something that is not as concentrated, we're still going to water down the solution, but it is not going to water it down as quickly. It's like if you have full milk and you want to water it down, well, one easy way to water it down quickly is to just add water, and then the milk gets diluted quickly. But if you have whole milk and you want to water it down, what you could do is just add 1% milk, for instance, and then the whole milk is gonna lose its concentration of fat, but it is, well, actually it is butter something. But anyway, it is gonna lose its concentration, but not as quickly as if we just were adding pure water. See, I'm beginning to talk about milk and the percentages of, the 2% when I'm actually not completely aware of that, because again, I do not know too much about chemistry. And when somebody doesn't know too much about something, they better stop talking about that something. So I'm just going to talk about math now. All right. So we start out the same way. Remember, we had half a gallon there it is, half a gallon of the pure chemical in the original 10 gallons. So again, remember, we start out with 10 gallons of a 5% concentration of a chemical, which means we have half a gallon, there it is, of the chemical. But now we're gonna add more pure chemical, but it's not gonna be all the gallons. We're gonna add 2%, so 0.02 of X. And X in this case will be the amount of the new solution we're adding. We should write it down ahead of time. I keep forgetting to do that. Let X be the amount of added solution. There we go. Okay. So that is the pure chemical point. So 2% of what we're going to add plus the half a gallon that was there to start with. Now, the solution will be in total 10 gallons that we start with plus whatever we're adding. There we go. So, and that should end up with a concentration of 3.5%, which is equivalent to 0.035. That's how we set up the equation. It is good to compare. It is always good to compare. So the way we set up our equation on example 1, when we were just adding water, notice that we have 10 plus X in the denominator, just as in here, but we have the 5 or the half gallon, but now we're adding a little more extra, 2% of the new solution, versus here we're not adding more of the chemical anymore. That is the difference. Everything else is going to be the same. So again, multiply. So 0.5 plus 0.02x will be 0.35 plus 0.035x. So we're multiplying this with the 10 and that with the x as we multiply the denominator. Now there's more things to subtract because we have an x and an x and a number without an x and a number without an x. So when we subtract 0.35 from both sides of the equation, we still end up with 0.15 as in the previous problem. But now we got to subtract 0.02 from 0.035. So that's going to give us 0.015. It's not necessary, but I prefer to put zeros before the decimal point. So here, there we go. And let's not forget the x. So solving this equation for x, we have 0.15 over 0.015. And we can do the same thing we did in the previous problem, multiply by 1,000. So that is 150 over 15. And of course, that is going to give us 10. So we need to add 10 gallons of the new solution. Yeah, so we need to add 10 gallons. Now, the original solution had a 5% concentration. So this is interesting. We have 10 gallons at a 5% concentration. We're going to add 10 gallons at a 2% concentration, and that's going to give us 20 gallons. What is halfway between 5? In this case, it worked out kind of nicely, because halfway would be 3.5%. If we average those two, but this only worked out well. That was a coincidence because 3.5 is exactly halfway between those two. Most of the time, that's not going to be the case. That worked out quite nicely. After the fact, and after we got 10 gallons. I realized, oh, wait a minute, that's the same as what we started with. So what's going on here? And yes, but most of the time, that is not gonna be the case. That was a coincidence. I should have probably taken a different number than 0.2 or 2%, but that's okay. All right, now, example 3, we're gonna increase the concentration. So we want to increase the concentration of the chemical, from 5% to 7% by adding pure chemical. And the question is, how much to add? Oops, how much to add? Okay, so again, this time I'm gonna think ahead and I'm gonna think, okay, let X be the amount of pure chemical to add. Okay, so remember, this is the same setup, the same starting problem. We had 10 gallons. So all of these examples are under the umbrella of starting out with 10 gallons of a 5% concentration solution. If we started with something else, then you have to adjust the numbers accordingly. All right. So we already figured we have half a gallon. We're going to add pure chemical. We had 10 gallons, and we're going to add pure chemical. So this is the volume, the total volume. It's pure chemical. And this is the actual amount of the chemical, which is, because it is pure, it is 100%. So by X, we mean 100% concentration. So it's 1.00x. And we want this to be 0.07 because we want to increase the concentration. Every time you're adding pure chemical, you're going to increase the concentration. We're not going to be at 5%. It's going to go up. It's got to go up because we're adding pure chemical. So the water, so we're going to water down the water. Okay. Instead of watering down the chemical, we're watering down the water, which is kind of weird, but it works. All right, so let's multiply both sides. So 0.5 plus x is equal to 10 times that, so that is 0.7 plus 0.07x. All right, so this is 1x, and this is a fraction of an x. So we want to subtract this guy from this guy. And we're going to have 0.93x equals, and then 0.7 minus 0.5 is 0.2, 0.2. Interesting. Let me double check. So that's 0.07x, and then 0.7. And then subtracting, we get 0.2, and subtracting, because this is 700ths, we end up with 93 hundredths. Yeah, it looks like we're good. So x equals 0.2 over 0.93. Multiply both the numerator and denominator by 100, and we get 20 over 93. And that cannot be simplified. No, we cannot simplify that in any way, form, or shape. So this is a fraction of a gallon. It's less than a gallon. This is a proper fraction. The numerator is smaller than the denominator. So that's it. So the exact answer, so we need to add 20/93 of a gallon of the new solution of pure chemical. So less than a gallon. If you put this as a decimal, I'm not going to do it here, even though I do have my handy calculator, because I want to insist in exact solutions. And as soon as we start writing the decimal, particularly for this answer, we're going to invariably have to add, we have to round up or round down. So this is the exact answer, and that's what we are going to box. So we need to add this. I'm going to figure this out as a decimal without writing it down, just so we have an idea. So 20 divide by 93, and that gives us about 22 hundredths of a gallon. So about a fifth. Yeah, it's about 1/5. You know, if this was 20 over 100, that would be exactly 1/5. So it's about 1/5 of a gallon. But again, we're not going to write down the decimal, because if we have a decimal, we have to round up or round down. And we really want to focus on the exact answer. So very little, we have to add very little, as opposed to in the previous examples where we had to add, 4 and change gallons or 10 gallons to water things down. Because we're adding pure chemical, we need to add very little. Okay. So now, okay, example 4. Okay, we add let's say a 10% solution, and want to end up with a 7% solution. The question is, how much to add? See, again, we're starting out with 10 gallons, so this is under the same umbrella, of a 5% chemical solution. So if we have a 10% chemical solution, this is much more concentrated. This is a stronger solution. When we start mixing it with this weaker solution, we're going to end up with something that is in the middle, between 5% and 10%. We want to reach 7%. Okay, so this is strong. This is weaker. We want something somewhere in between. So how much of this strong one do we need to add to get this much in between? All right. So I was going to do 9, but then I thought that's not going to work too well, because then that's going to be sort of 7 is going to be right in between 5 and 9. So we would have to add 10 gallons. That's what I'm guessing based on example 2. But I think this is going to be twisted enough that the answer is not going to be as obvious. Okay, so let X be the amount of 10% solution to add. It's a good idea to get into the habit of writing down what the variable means. It is time consuming. We get lazy, I understand, but it is still a good habit to form. So we had 10% solution. Okay, so same kind of thing. We had half a gallon to start with in the container. we're going to add a solution, an amount of solution of which 10% is pure chemical. So this is the pure chemical as we keep adding more of this solution. The total volume is 10 gallons that we started with, but then we're going to add the X gallons of the solution. And we want to end up with is 0.07. Okay, please compare this equation with equation in problem 3 and in example 2 and in example 1. It is a very good thing to do, to compare. Okay, so multiply 0.5 plus 0.10x is equal to 0.7 plus 0.07x. Okay, so we have 7 and 10, so we can subtract this from that, and that is going to give us 0.03x, and then 0.7 minus 0.5 is 0.2, 0.2. So x is 0.2 over 0.03 multiplied by 100, so we have 20 over 3. Let's rewrite this as a mixed number. 3 goes into 20 6 times, and there are 2/3 left over. So we need to add 6 2/3 gallons to obtain 7% concentration. Yep. Because this is pretty strong. This is double the concentration. So we need to add, not 10 gallons, but 6 2/3 of a gallon to obtain precisely and exactly 7% concentration. So this is kind of a neat problem. We will focus on those 4. There's one more example I want to illustrate here. Perhaps we don't necessarily have to finish it right now, but I do want to illustrate this. So let's say you want to replace, okay, so we started with 10 gallons. Now we start with 10 gallons of 5% solution. So that is the concentration of the chemical, 5%. Okay. Pretend we want to end up with 10 gallons. See, in all of these examples, we end up with more than 10 gallons. In the first example here, we had 10 gallons, and now we end up with 14 because the 10 we started with plus the 4 is 14 2/7. So we end up with a significant amount of more liquid than what we start with. Here, in the second example, we end up with 20 gallons. In order to water down the liquid from a 5% concentration to a 3.5%, we end up with more. Even if we want to increase the concentration, we end up with more. So even though this is less than 1 gallon, remember, we started with 10 gallons. So we have now not quite 11 gallons, but maybe somewhere in the neighborhood of 10.22 gallons of the liquid. Now we have the concentration we wanted, which is 7%, and we end up with more. The other question here is, or the other problem rather here, we end up with 16 2/3 of a gallon. So we end up with quite a bit more. But let's pretend we have a container, and we cannot add more to it. We still have 10 gallons and 5% concentration. And so there is the liquid, but we cannot add more. We don't have a bigger container, in the previous examples, this is what's going on. Let me kind of illustrate what's going on. So we have the initial 10 gallons total, like in this case. We need to pour that into a big container. And then we need to add the 4 and 2/7 in this big container that can hold 14 or 15 gallons. And then if we need to only have 10 gallons, we mix this up and then we put this back into the 10-gallon container. And then there's going to be some left over, of course. So in order to physically do this, we have to have the initial container plus a bigger container. Or I guess the other alternative is that we have to start with a big container that is not full at 10 gallons. That's, I guess, the other way to do it. But let's add a constraint to this. Let's pretend you have a container that holds 10 gallons and that's it. You have smaller containers, but you don't have a big container. So we can keep adding more to it. So, and let's say we want to increase. We want to increase concentration from a 5% to 7% using, and I'm going to change this, an 11% solution. All right, so we got the 10 gallons, 5% of it, so half a gallon is pure chemical, but this is all mixed. And we got a container, or we have a couple containers, but we have a 7%, rather an 11% solution. So this is pretty strong. And we want to water this down to 7. So in this case, we have to scoop some out because we don't have a big container. So we have to scoop some of it out and then refill it up with this strong solution. So we're going to scoop some of the 5% out and then refill with an 11% solution so that we end up with a 7% concentrated new solution after we mix it. So the question is, how much should we replace? How much should we scoop out and replace that with this strong solution? So we end up with 7%. Boy, that seems very difficult, but actually it isn't that bad. All right, so this is the thing. In all of these problems, we have this kind of situation. You know, the pure over the total amount is going to be equal to the desired concentration. So we want a 7% concentration. Now, here's the thing. We have 10. We're going to scoop out an amount of liquid of this 10 gallons that is already mixed of the 5% solution. And then we're going to replace it with the same amount because we want to end up with the 10 gallons. So we're going to scoop out and pour that amount in, the same amount, but of a different solution, of the strong 11% solution. So you're going to say, wait a minute, 10 minus x plus x is 10. Yes. So the 10 is going to be preserved. We start out with 0.5 gallons of the chemical. We're going to take away 5% of the chemical. We're going to scoop up an amount, but that amount that we scoop out is 5% the chemical. So when we're scooping out, I don't know, let's say these are 2 gallons. When you scoop out 2 gallons, 5% of that is pure chemical because it's all mixed. But then we're going to add 0.11 of the same volume. So the X is the volume that we're scooping out and we are adding in, except that we have the amount that we're scooping out is only 5%. The amount that we are pouring in is going to be 11%, which is really neat because In algebra, you can actually add those two together. I keep forgetting, and it's a bad habit not to have. Let X be the amount of solution scooped out and poured back in. All right, so it's the same amount because we want to end up with 10 gallons. All right, now let's just use a little bit of algebra. 11 minus 5 is 6. So combining those two terms, we really have 0.5 plus 0.06x. And then just 10 in the denominator. Because the two x's cancel off. I think this is a really, really neat problem. All right, which makes sense. You know, think about it. You're replacing a 5% solution with an 11% solution. You are gaining 6% for every gallon that you are replacing. All right, so this is actually not too bad of an equation to solve. Multiply by 10, so 0.5 plus 0.06x is equal to times 10, 0.7. So that means that 0.06 is equal to, oh, I missed the x, 0.2. And that means that x is 0.2 over 0.06. We can simplify the 2 and the 6, or we can multiply by 10 first. That's the same, rather by 100. So that is going to be 20 over 6, which is the same thing as 10 over 3, which is 3 1/3. So we need to replace 3 1/3 gallons. All right. So again, you have 10 gallons of a mixture that is 5% concentration of a chemical, but you don't have a big container to mix more of it. So what we have to do is scoop up some and then put a stronger chemical that is 11% concentrated with the chemical. And we want to end up with 7%. We started out with 5% and we want to end up with 7%. Well, that means that we're going to end up with the same volume. So the volume is the same. And every time we're replacing a gallon of the new chemical with the old we're going to replace some of the old with the new chemical, with the new solution. And every time we are doing that, we're gaining 6%. Okay, because this one is 11 and this one is 5, so the difference is 6. That makes sense. Yeah. So when we solve this equation, we need to add 3 1/3 gallons. So we got to scoop up, you know, a third of the tank. We got to scoop, but we're assuming this is all mixed. We scoop up a third of the tank, exactly a third, and then we refill it with this, and now we got ourselves a 7% solution. I think this is really, really neat that we are able to do this application with this basic mathematics. All right, we'll stop the video here.